We saw Zephyr bindings briefly in the previous episode. They create an interface for our device tree specifications and help connect the device tree to device driver code. In this episode, we're going to dive deeper into bindings files. In the process, we'll create a simple analog-to-digital demo on our ESP32. In the last episode, we looked at the device tree syntax and how it's used to configure hardware and drivers. This time, we'll examine bindings more closely and how they are used to connect the device tree to device driver code. Note that they are unique to Zephyr. Linux does not use bindings files. With CMake, kconfig, device tree, and bindings, we are building up to writing our own device driver code, which we will get to in the next episode. Before diving into the actual bindings files, we need to understand a little bit about the hardware we want to use. For this episode, we will use the same hardware setup that we've been using for the series, but we'll focus on the 10K potentiometer connected to pin 1 of the ESP32-S3 DevKit-C to demonstrate analog-to-digital conversion. For the challenge, you'll also want an LED connected to pin 13. The first thing we need to do is figure out which analog-to-digital converter pins are attached to the external pins that we want to connect to. So bring up the ESP32-S3 datasheet, also known as the technical reference manual, and we're going to scroll through all of these chapters. Let's see, I think it's in 39. Here we go, SAR ADCs. If we go to part 4, let's see, you got to scroll through all of this. Here's the table I'm looking for. We can see that the ESP32 has two ADC peripherals. There's ADC1 and ADC2, and you can see the channels associated with those and which pins they are attached to. Unlike other peripherals on the ESP32, there's no pin muxing. We can't say channel 2 to GPIO 11. These are hardwired into the controllers. Now, if we go to section 6, we go to this register summary. Let's see, it's somewhere in here. I want to say it's in part 3. Oof, okay. Oh, there we go. It was that first table I looked at. There are two configuration registers, one for ADC1 and one for ADC2. These are offset from the base ADC memory. If we go to table 4.3 and you look through here for the ADC, which I believe is 6004000, here it is. So it would be this address plus those offsets. Next, we want to find out about the peripheral drivers, sort of like we saw in the previous video. So make sure that your Docker container is running, log in with VS Code, however you choose to do that, or run everything locally. Let's go into the Zephyr base directory. We're going to go to DTS extensa, let's go to espressif, and under ESP32-S3, we've got this common device tree source include file. There's a bunch of stuff in here that sets up the ESP32-S3 peripherals, and we want the ADC, so let's search for that, and we see ADC 0 and 1. Zephyr likes to do things with base 0, so this is actually ADC 1 according to the datasheet, and this is ADC 2. By convention, this node name uses @ and the memory address, which should line up with the memory address we saw in that table on the datasheet. And then the reg property should be the actual place in memory, which the drivers use to figure out how to communicate with that peripheral on the ESP32. There's also a size cell here that's 4, so 4 bytes long, or one word, which means that the next address for ADC2, which is ADC1 in Zephyr, should be 0004, and sure enough, that's what we see. Take a note that both of these are disabled by default, which means we will need to enable them, or set this to OK, in our own overlay file. If you're curious about where these values come from in all of these subnodes, if we go back up to this SOC top node, which is right here, you will see that Zephyr specifies that we need to include these special keywords for properties called number address cells and number size cells. These tell the associated peripherals attached underneath the SOC cell that they should have one address cell and one size cell, and that's exactly what we saw. This is the address cell. It should be an unsigned 32-bit integer, and there's one size. That is the size in memory that the driver should expect this peripheral to take up. So let's head back to ADC. And what do these other properties mean? What do these tell us? Well, we need to dig into the bindings files to find out. Notice that this compatible gives us a clue as to the name of the bindings file. So if we search for that file, espressif, ESP32-ADC.yaml, we can bring up the bindings file that's associated with it. Note that the file is named after the compatible by convention. It doesn't have to be. What Zephyr actually cares about is what's in this required compatible field here in this YAML document. If you need a review of the YAML syntax, I highly recommend this YAML tutorial from spacelift.io. If you go through here, you can get a great example of a very simple YAML file. It is essentially just a bunch of key value pairs, much like you'd find in a Python dictionary or in a JSON string. So you've got the keys over here, you've got the values, you can have arrays with these dashes, so this domain would be an array of these strings or other values. And then you have an array here under tutorial of YAML JSON XML, and you've got individual key value pairs under each of these array elements or entries. So back to our bindings file, you can find properties that are unique to the ESP32 ADC controller. This description gives us a really good overview for what espressif requires for the different resolution options available to each of the ESP32 variants, as well as how to set the gain for the analog to digital converter. This is a little bit tricky. The ESP32 is notorious for having a not very good ADC. It's both pretty inaccurate and has a limited range. Let's take a look at their docs. So if we bring up the analog to digital converter doc on espressif's documentation page, you can learn a little bit more about their ADC. You'll notice here, even in the docs, it says that the vref is set to an internal 1.1 volts, but this can vary. So espressif just says it's about 1.1 volts. So we're going to assume that for now. If you set no attenuation, you can measure up to that vref, but you lose a lot of accuracy after about 0.95 volts. So consider everything in that top range between 0.95 and 1.1 volts to be very inaccurate. If you set the attenuation to 11 dB, you'll get a range from about 0 volts to about 3.1 volts. That's the usable range that espressif recommends. In my experience, this is very not accurate, but we're going to get something good enough for what we need to do. There's some more information in here about calibrating your ADC. As you can see, there's a lot of non-linearities. My recommendation, however, is if you want an accurate ADC, get an external chip, like an I2C chip, to do it, rather than trying to go through all the headache of trying to make this work, unless your board is really budgeted limited in space and price. Or, like with this demo, you're okay with it being very inaccurate. Back in our bindings file, you see a note down here that says we can use the Zephyr predefined value, that's the ADC gain 1/4 or 1/4. That tells the espressif driver that it should set the attenuation to 11 dB. Now, gain of 1/4 is not exactly 11 dB attenuation. 11 dB attenuation is actually closer to something like 1 divided by 3.54 rather than 1 divided by 4, but it's close, which is why espressif is saying use this value. But know that it's actually 3.54, and that calculation is going to come in handy in a minute. The rest of this defines the required and optional properties for the node. You can think of this like an interface. When the bindings file describes these properties, you can expect them to show up here in the device tree. We have unit, channel count, and number I/O channel cells, which lines up with the properties here. Notice that some of them are required, number I/O cells is not, but it's already set to a constant of 1, which means that defining it in the device tree here is probably redundant. My guess is it's here just to be clear about what developers can expect for the number of cells when defining a p-handle array, which we will look at later. I'm going to Control-Z out of this, so nothing gets saved that I wrote. And you can see that it includes this adc-controller.yaml, so let's look for that, which is right here, and it's part of the base Zephyr ADC bindings. So generally for a board support, you will include this adc-controller.yaml because it provides a common interface for your ADC drivers. That's, of course, assuming your controller has an ADC. This keeps going down. It includes base controller.yaml. So we'll look for that. This is a very common interface that defines a lot of the reserved keys or reserved properties that we've come across. Things like compatible, reg, interrupts we won't play with right now, but we will come across those later, label, address cells, size cells, and so forth. So let's close out of base.yaml. We don't need that anymore. Specifying the I/O channels is one way to configure an ADC channel. You'll see it in some of the samples, but I'm honestly not the biggest fan of how that works, so I'll show you a different way to define a custom channel subnode instead. However, note that because it is set here and it's required true, the ADC driver still has to define this property. And you will see this in a lot of overlay and YAML files that define how the driver should work with the ADC. Looking back in that ADC controller, you will see size cells and address cells. This tells us the array size for the reg property for subnodes underneath an ADC node. Unlike what we saw under the SoC, those peripherals, this is not the same as an address in a memory address. It refers to the channel for that ADC controller. So when we're talking about peripherals in a controller or specifying memory locations, note that address means a memory location and size means the size of that memory. When we're talking about devices hanging off of a bus, like an ADC channel or a device on an I2C bus, this is going to refer to the address on that bus, or in our case, the channel. Because this isn't memory, there is no size, so you can expect size cells to be set to 0. Child bindings define the properties for any child nodes under a parent node, like our ADC controller node. Take a look at this description and you'll see that subnodes must be named channel, otherwise the driver is not going to know what to do with them. In most cases, it's up to you, the developer, to figure out what to name or just choose some name randomly for subnodes. But this is why it's always crucial to look at things like these descriptions, because in this case, it gives you a defined subnode name that you need to use. Otherwise, the driver's not going to work and the compiler will probably yell at you. In each of your subnodes, there are some required properties. Reg is required, and it has a special meaning when you have an array because it looks for the properties above it to define the number of address cells and the number of size cells. This is a special reserved keyword in Zephyr, and it looks for these properties to know how many cells are in this particular array. I find this a little confusing because you're basically saying that the length of the array is defined not in this property or even somewhere in the child bindings. Rather, you have to go up to the parent properties to find out what the length of that array is based on these properties. Some of these other properties list a Zephyr comma prefix. This works as a sort of namespace to keep property groups separate. So these are often things defined by the Zephyr system and not by, say, a vendor. Of these, you'll see that gain is required, reference is required, and acquisition time is required. What's interesting here is that these actually list enums, which means you have to choose one of these values from this list of strings when you're setting the gain. This gets passed to the driver, which is why we couldn't set something like the decibels for attenuation. We have to choose ADC gain 1/4 or one of the available ones as listed in the espressif description. So this is why it's super helpful to go through these files for specifically your vendor for your board and read these descriptions, because there's some gotchas in here if you're not paying attention and you're just trying to use some other sample from another vendor. We only have one reference voltage available for us for the ESP32. We will see that be set, and I believe that's the ref internal. We won't have to mess with that, but it will be set for us. There's also the acquisition time. We're just going to use the default that ESP32 sets for us. Then we have some of the optional values. We've got the vref millivolts. This can be set in our, say, overlay file or in the board DTS. That gives us a number for various calculations. In fact, we're going to set this and use this as an example to see how to pull out properties from our device tree in our code. We also have the resolution. According to espressif, this needs to be set. For us, it has to be set to 12. And we will see how to get this property in code as well. One way to think about these includes, when we include things like this ADC controller bindings file, we are extending the standard Zephyr ADC bindings by adding our own properties because, for example, the ESP32 device driver needs some unique properties in order to work. This adds the unit and channel count properties to the ADC nodes. It also sets the number of I/O channel cells to 1. Whenever you see a number of something cells like this, it usually means that you or the vendor is specifying an array length somewhere. And in that array, you will have elements, or what DeviceTree calls cells. Often you will see these specifier cells. They exist outside of these properties and then specifies the properties in this YAML array. So for example, this specifies that the cell following an ADC cell when listing an I/O channels property should be considered an input or channel number. Let's take a look at an example. We will go to our Zephyr RTOS source code. We're going to go to samples. We're going to go to drivers, ADC. We're going to go to DeviceTree, ADC DeviceTree. Then we're going to go to boards. And then we're going to look for, there's an ESP32-S3 in here. That's the DevKit M Pro CPU. So it doesn't match up with our dev kit, but this has a very good example for us. And I highly recommend looking at the samples folder in Zephyr for guidance on how to use things like device trees and the drivers to make things work for your board or something close. In this overlay, you can see this really odd node that's underneath the root node called Zephyr, user. This is a special node that Zephyr has set up for users and developers to store custom properties. In this case, they are storing I/O channels as a p-handle array with 2 elements. Each element is a p-handle with an argument. The p-handle, like ampersand ADC0, refers to a node defined somewhere else, and the following 0 acts as an argument known as a cell. Here they're giving it the address of the ADC node, which refers to this whole node, and then they're specifying channel 0. So in essence, this element of this array refers to this node here, this channel. 0 here refers to what's in the reg property here. Don't worry about that @ symbol. Remember, that doesn't particularly matter. But the name channel does have to exist for this subnode name, as we saw in that description for the ADC controller. Similarly, we have ADC1, so there's 2 channels on 2 different pins. This is referring to this ADC1 node and also channel 0, which you should expect reg to be set to integer 0. I find this configuration a little confusing, so I'm going to show you a different way to do this. But if you go and look at the source code for this example, which is right here, you will get an idea of how to get that information from the device tree and then configure those channels and then read from those channels. This is a really good way to do it if you've got a bunch of channels, because you can just store them inside of an array like this and then loop through all of those channels. Now let's go to drivers. That's the actual drivers, not in our samples. We're going to go to ADC and we're going to look at ADC ESP32. This is a driver written by espressif that talks to the ADC peripherals on the ESP32. The important thing to note here is this DT-DRV compat, or device tree driver compatible. This name should line up with this name. However, because C does not work with characters like commas and dashes, especially for things like macro symbols, it converts it all to underscores. So anytime you see something like a comma, know that in C that's going to be an underscore. Same thing with a dash. So if you convert those to underscores, this name lines up with this name. And the Zephyr build system, when it's looking for the associated driver files, goes through any modules you have included, like external modules like we will do in our demo, or it goes through the drivers folder internal to Zephyr and tries to find something that matches the macro symbol here, set to DT-DRV compat. If you look through these includes, you'll see this adc.h. Let's go to that file, and you will find a bunch of common ADC functions and macros in here. We'll be using these in our demo. One of the important ones is this ADC DT spec. I'm going to search for it and hopefully find this definition. So I'm going to find this definition here. There it is. This is a struct that we will use to hold a lot of our information about the ADC. We will fill out information about the ADC, most of it at least, in the device tree or in our overlay file, and then we're going to populate this struct in our code so that we can access this information in our code. Let's scroll on up, and you can see this other one where we see device.h. So let's go to that file. In here you should find I believe it's a struct device. That's good enough. We can go to the definition here. And this is what we're looking for, struct device. This is a common struct for holding generic device info. You will see some configuration information. This is usually filled out from the device tree. An API is a collection of function pointers. And if we go to our adc.h, we can look for ADC driver API. You will often find something like this that's an underscore API. This is a struct that's going to hold our functions. And it looks like this also holds our reference voltage. So if we go to this and we look at this, this is setting up function pointers for us so that we can implement them in our code. If we go back to our ESP32 ADC driver, near the bottom, let's see if I can find this, you can see where the functions, the individual functions from the driver, are assigned to that device driver API struct, which is right here. So these functions are assigned to these individual fields, and you can see that ref internal is populated by this default vref internal from ESP32. They go ahead and define that for us. So once again, this struct exists. So if we go to adc.h, you can see that it's basically requiring these two functions for the API. Your driver's job is to implement those functions, then assign them to these struct fields. So if we look for this channel setup function, you can see it right here. This API, if we scroll back down, is called API ESP32 driver API. This is passed to this device DT instantiate or instance define. This is a macro used to create the individual functions, data, and other structs used for an instance of this driver. This is some macro magic that we will dive into later in the next episode. But know that this is how Zephyr accomplishes instancing, much like you would find with something like object-oriented programming, without relying on an actual object-oriented programming language like C++. This is all in C. This has the effect of generating code for each version of the driver you have. So for example, if you have multiple ADC or ADC channels, this gets unrolled into different functions for each instance. This bears another resemblance to object-oriented programming in that the ADC is a type of device and it inherits various properties from it. The ESP32 ADC driver implements the API set forth by the ADC interface. By having both expansion macros to do instancing and this idea of common interfaces with some sort of inheritance, you get close to something like object-oriented programming without actually using something like C++. Hopefully this helps give you an idea of how drivers are implemented, and we're going to dive into creating our own demo to use the ADC driver so you can see all of this in action. Let's close down the files that we've been looking at, and we're going to go to our workspace because we're going to finally actually write some code. Go into our apps, and let's make a new folder. We're going to call this 05 ADC Demo. In there, we're going to make our boards file where we can put our overlay files. I'm going to make my devkit.c overlay file. The first thing I'm going to do is describe some aliases. We're going to need to alias our ADC 0 node because we're going to be using that peripheral, and we're going to need to alias the individual channel. We're going to get that information in our code and use that to read the analog-to-digital converter values. I'm going to make a note here that we are enabling ADC1 or ADC0 in Zephyr because it's 0-based, channel 0. And if you remember from our pinout table, that is connected to pin 1 or GPIO 1 that's on our board. As we saw in that device tree source file, the ADCs are both set to status disabled, so we need to turn those on, or at least the one we're going to be using, we need to set that to status equals OK to enable it. Then we're going to define our subnode of channel. Remember that name is required according to that description we saw, and we're going to define some properties in here. The reg property needs to be set to our channel number. In this case, it's 0. And if you remember, we need to set gain to this gain of 1/4. So if we go and search for it, we know that's the vendor first, and there was the file we looked at earlier. There's the note in here, and these are the available ones for us. It's a limited set of values of what's globally available to us from the rest of Zephyr. So we have to choose one of these, and we're gonna go with 11 dB attenuation to give us the maximum range for that ADC. I don't think we have many choices here, so we have to set it to the internal reference. Remember how I said that the attenuation actually gives us 1/3.54 instead of 1/4? That has the effect of increasing our reference voltage from 1.1 volts to about 3.9 volts because of that attenuation factor or the gain factor. So in fact, I'm actually going to update this because 894 is slightly more accurate, although it doesn't matter. As you will see, this ADC is not the best. This is a number that's been defined for us. So if we bring up this ADC controller again, let's get rid of that bracket. And we can find the acquisition time. You can see that we can set it to ADC ACQ time default to use the default settings. That's fine. The ESP32 should have that set for us. I don't think the espressif drivers do much with this resolution setting, because it is an optional setting, and from what I can tell, the ESP32-S3, it's already set to 12 anyway. But by filling this out, we can use this in code for some calculations. Don't forget, we need to end everything with semicolons because DeviceTree. Let's save that file, and we are going to add src for source, and in there, we're gonna create main.c. We're going to include our normal standard input-output and our kernel header files. We also want to include the ADC header because we want access to the functions in there. Remember that this provides a common API for us to use so we can create portable code. We don't need to call the actual ESP32 driver functions because this will call those for us. We're going to sleep so we don't just overload our console. First thing we're going to do is define this macro that calls the DT alias macro, which comes from DeviceTree.h. This allows us to get a node identifier from the device tree, and we do that by passing it in an alias, hence DT alias. So by passing it in my ADC channel, remember that these dashes get converted to underscores for the macro symbols. It's going to reference this node for us, and it's going to get all the information from this subnode. Let's go back to our code and keep defining device tree stuff. Then we're going to get a device struct. We can go to that definition. It's in device.h. Remember, we looked at this. This is the config API that gets filled out for us from the device tree. And because ADC is a type of device, it's using this interface so we can count on an ADC being of type device. Next, we're going to get this device DT get, which is also defined in that header file. This gets a node ID, which we have to get by using that DT alias. So we get the reference to that node. In this case, it's the my ADC node, which if you remember, points to this ADC 0. So it's getting all of this information. It's then going to fill out this ADC device struct. If we dig into this macro, and you see this macro keeps going, and it just keeps going. Essentially what it's doing is it's getting the information from here and filling out this device struct properties for us. Here we go, here's one. So I can go to this definition, click on that, and you can see that information again. Just like we filled out the struct information from this device that was defined from this node here, we want to do the same thing for our channel information. Rather than coming from device.h, which is this interface, we have the ADC channel configuration. We can go to that definition. That's in adc.h. This has those other properties that are defined for us, like the gain, reference, acquisition time, resolution. And if you look through those, you can read about each of those and how those get filled out from the device tree. But now we have access to the ADC, which has our API, the functions we can call, and our channel information. Note that I used a common macro here. We're going to use this macro later in code, but if you really wanted to, you could just replace it with something like that. But I'm keeping the code a little bit shorter. Let's define a few variables in our main. We need a return value. We're going to have a buffer to keep our ADC values in. Then we're going to have the value of the ADC and vref both in millivolts, so we can print both the raw value, that's the 12-bit ADC value, as well as the voltage in actual millivolts. A very simple demonstration is how to get device tree properties from the device tree. In this case, our overlay file that's defining the Zephyr vref millivolts property inside of a node. We can use this dt-prop macro that's defined in DeviceTree.h. This allows us to access a property and get the value from that property. We need to give it a node ID, which we get from this dt alias that refers to my ADC channel, which once again, that resolves to this node. Then we want to get the Zephyr vref-mv, which refers to this property right here. And once again, the comma and dashes get converted to underscores when we're referring to this symbol. So this is not an integer or a string or any variable like that in C. It's just a symbol that the preprocessor knows what to do with when expanding this macro. And note that you can define custom properties in the device tree. It would just store it in the device tree, and then you can just access it in code using this dt-prop macro. When we actually do an analog-to-digital conversion, Zephyr wants us to do this thing called a sequence. And the information is stored in this sequence struct, which is defined in adc.h. So we can bring that back up, adc.h. And I don't know why IntelliSense does not want to go there, but we can copy this. We can go to it. We can find the definition. Forward declaration. Where is the actual definition? Here we go. You can see how this creates a sampling sequence, and it's just some information about that sequence. But we do need to fill out these fields. So the first one is our channels that we want to sample, as I believe this allows us to sample multiple channels at once using a single device controller like ADC 0. So you could bit mask them, but we just want one channel, which in this case is going to be channel 0. Remember that ADC channel comes from this config that we have here. The channel ID is populated for us in the driver code, but it should refer to this register property here when we set the channel number. We're then going to assign where the output of that ADC goes. In this case, we're setting it to our buffer. We just created an unsigned 16-bit integer. Remember, these are 12 bits, so it should fit in a 16-bit integer variable. Like with anything in C, it wants to know the size of that buffer. In this case, it's just the size of a 16-bit integer. And finally, we want to set the resolution. If I recall, you don't actually have to set this in this sequence, but it's a good idea because we might want to use this in code. So we're just going to pull that property out like we did previously with the reference voltage from our ADC channel node. A very common pattern you will see when working with Zephyr drivers is this is ready, or in our case, because it's device is ready function. This makes sure that everything was called during the initialization in the device driver, and it's ready to go according to the Zephyr backend. Next, we need to configure the ADC channel, which we're going to do by calling this ADC channel setup. We pass it in our ADC peripheral configuration struct, as well as a pointer to our channel struct. So we need to pass it in both. If we take a look at that definition, which it can't find, but we can probably find it in here. Where is that setup? That's from DeviceTree. And you can read more about this function. It is required to call this function and configure each channel before it is selected for a read request. So yes, we do have to call this because this then calls the code necessary to set up the channel. Back in our source code, let's continue. And we finally get to our super loop. In there, we're going to read from the ADC. To do that, we're going to pass in the peripheral struct, in this case, the ADC, as well as a pointer to our sequence struct. So we only use that channel configuration that we set up here as information passed to our sequence. That sets up the buffer in configuration where everything gets done for our set of channels. And when we read the ADC, we pass in that sequence. Next, just for fun, let's calculate the actual ADC value in millivolts by taking whatever's in that buffer, multiplying it by our voltage reference in millivolts, and dividing it by the maximum value for our resolution, which is 12 bits or 4095. Well, actually we want to add one, so 4096, hence we 1 left shift 12. Then we want to print the ADC value. We're going to print both the raw value, that's just the buffer, as well as our calculated value in millivolts. And finally, to top everything off, we sleep it for, I believe it was 100 milliseconds before doing this whole thing again. With our code written, let's save that. And like any good Zephyr project, we need to create a cmakeLists.txt. And we will type out our boilerplate cmakeLists that just sets the minimum version, finds the Zephyr package using the environment variable, names the project ADC Demo, and adds our main source code to the app target. Let's save that. And then we need prj.conf, which is required for every Zephyr project. I could take you through the process of using menu config to figure out what we need to enable here, but you could also dig through the source code a little bit. And if you go to drivers, ADC, I think it's somewhere in here, there's the kconfig. So this gives us an ADC option, and it enables all these other variables for us. If you take a look at drivers cmakeLists.txt, you will see this add subdirectory ifdef that we have done before, and you will see config ADC. So we need to enable this ADC symbol in kconfig in order to turn everything on. Feel free to dig into other options, but honestly, this is all we need right now. So let's close that. We'll add this to our prj.conf, and we will set this to yes to enable it. Let's save, and we should be ready to build. Let's bring up a terminal in our workspace. We're going to go to apps. We're going to go to 05 ADC demo, and we're going to use West build to build our project. Let's wait a moment to let this happen. Uh-oh, we have a problem. If we look at our channel, so let's go into build. Let's refresh our files. Let's go to build. Let's go to Zephyr. Didn't even make a DTS for us. What's going on here? It has something to do with our ADC. So that's ADC 0 and channel 0. So it's probably about this node here. It has length 4, which is not evenly divisible by 12. So address cells somehow got set to 2, and size cells got to 1. So that has to do with ADC. If we go back to our common here, which has all of this information, let's look for that ADC 0. Okay, that's not setting address or size cells here. Let's go to our YAML file. Okay, that's not being set here, so maybe they're just not getting set. All right, so it should be set to 0 and 1. So according to this, our reg property in this overlay file, which is right here, that should just have address 1, size 0. That's fine. But it looks like somewhere address cells or number address cells is getting set to 2, number size cells is getting set to 1. This is part of the thing that makes device tree stuff quite convoluted, sometimes confusing, and sometimes very hard to debug. There's some file somewhere that is setting address cells to 2 and size cells to 1, which means we need to overwrite that. So we're going to overwrite whatever is setting those, and we're going to go back to what was set as constant values in this adc-controller.yaml. It should be using these values. I'm not quite sure why it's not, so we're just going to set them here in our ADC node for our overlay file. Let's save that and try to build again. All right, it looks like it built that time. Let's bring up a terminal in our host computer. Make sure you are in your virtual environment and you are in the Introduction to Zephyr repository. We're going to use the ESP tool to flash our chip. Make sure you select the correct COM port and let that happen. We're then going to connect to the serial port on our ESP32, and you should see the raw value and millivolts being printed out. And if I twist the knob, you can see those being changed, which is awesome. Now, if we go all the way to 0, that should be 0. If I crank this all the way up, that should be 3.3 volts, but you can see that we are off by like half a volt here, which is really frustrating. That's part of the thing that the ADCs on these ESP32s are notoriously inaccurate. And we can press Control bracket to end that. If you'd like to learn more and dig into this, I highly recommend checking out this Practical Zephyr DeviceTree Semantics blog post on Interrupt. In it, Martin goes through a lot of the things we just looked at, how overlays work, how Zephyr looks for the matching bindings files, and how it uses that to find the associated device driver source code. You also get a deeper look at some of the device tree semantics if you'd like more practice with that. And now for your challenge. Your challenge is to assign a pulse width modulation or PWM controller to the LED pin in the device tree and write an application that controls the LED brightness whenever you twist the knob on the potentiometer. If you want some hints, go to the Zephyr RTOS source folder, go into your samples, which are down here, look for basic and Blinky PWM. The boards here have some good ESP32-S3 overlays that you can look at for examples. Note that you will need to specify a PWM LEDs node with the PWM's property. This has a p-handle array that refers to the LED controller node and sets some parameters here. This configures the channel, period, and polarity for the PWM. LEDC0 is the LED controller name, and that should be defined in your SOC DTSI file. Now let's look at DTS. We're going to go into Extensa, that's not part of the bindings file. We're going to go into espressif and the ESP32-S3. I want to say this is the DTSI. It looks like it wants to include the common. Here's that common DTSI we were looking at for our chip. If we search for LEDC for the LED controller, you can see that it's a predefined node here with some properties that have been set. It also uses the espressif ESP32 LEDC compatible bindings. So as we've done before, we can copy that. We can look for that YAML file to bring up the bindings. And this description is very good at telling you how to configure this to create an LED PWM controller. Pin-CTRL is a node that allows us to assign pins to functions using the pinmux property. So let's go back to our sample with basic, Blinky PWM, and let's find that ESP32 DevKit M Pro. You can see this pin control node in use here and how it's assigning GPIO2 to channel 0 of the LED controller. Now if we go to DT bindings, let's close some of these. Now if we go into our include, we go to DT bindings. You can find pin control, which is right here. If you go to the ESP32-S3, you can find the pin control header. That's where these macros are coming from. So in this overlay file, you can copy this. In here, you can find that this is related to the LED controller, and it's how you assign various GPIO pins to that particular controller and that channel. And there's channel 0. You can see it's repeated here for channel 1, and that's part of the reason this file is so massive. It's pretty much every possible combination of device peripheral and the available pins that it can use. For example, you probably want to use LEDC channel 0, I recommend. You could probably use a different channel if you wanted to, and GPIO 13 because that's what we have previously connected our LED to. In addition to this, you will also need to enable the PWM driver in kconfig, but I leave that up to you to find. While we did not write our own bindings, I hope this helped you see how they are used to define DeviceTree node interfaces. Next time, we'll get a chance to write a bindings file when we make our own device driver. See you then.